So let's talk about algebra, and I mean really talk about it, like the whole story, from the very beginning all the way to what we know today. Because here's the thing, most of us were forced to memorize formulas and solve for x in high school, but nobody ever told us that algebra has one of the wildest origin stories in all of mathematics. We're talking thousands of years, multiple civilizations, international drama, duels to the death, and some seriously brilliant minds who changed how we think about pretty much everything. Before we jump in, I need to set something straight. When you hear the word algebra today, you probably think of equations with x's and y's, right? Maybe you remember solving quadratic equations or factoring polynomials. But algebra hasn't always looked like that. In fact, for most of human history, algebra looked completely different. There were no symbols, no letters, no elegant formulas written on a chalkboard. Just words, lots and lots of words. Think about it. Imagine trying to solve an equation without being able to write x plus 5 equals 8. Instead, you'd have to say something like, the thing plus 5 equals 8, every single time. That's what early algebra was like, and somehow people managed to solve incredibly complex problems using this method. So, where do we even start? Well, let me take you back, way back. We're talking ancient Babylon, around 1900 years before the Common Era. The Babylonians are living in what's now Iraq, and they're dealing with practical problems. How do you divide land fairly? How do you calculate interest on a loan? How do you figure out how much grain you need to store for winter? These weren't abstract math puzzles. These were real-world problems that affected people's lives, and the Babylonians figured out that they could solve them using what we'd now call algebra. They developed methods for solving equations, even quadratic and cubic ones, and they wrote everything down on clay tablets. These tablets survived thousands of years, and when archaeologists dug them up, they found something amazing. One of the most famous is called the Plimpton 322 tablet. This thing was created somewhere between 1900 and 1600 BCE, and it contains a table of what we now call Pythagorean triples. That's way before Pythagoras was even born, by the way. The Babylonians were working with advanced mathematics that wouldn't be rediscovered in Greece for over 1,000 years. But here's what's wild about Babylonian algebra. They didn't care about exact solutions. They were happy with approximations. They used something called linear interpolation to get close enough answers for practical purposes. And you know what? That makes sense. If you're a merchant trying to figure out how much to charge for grain, you don't need 12 decimal places. You just need something that works. The Babylonians also developed what we'd call algebraic operations. They could add equals to equals, meaning if you have two things that are equal, you can add the same amount to both sides and they stay equal. They could multiply both sides of an equation by the same thing. They could manipulate equations in ways that seem obvious to us now, but were absolutely revolutionary back then. Meanwhile, over in Egypt, people were also doing algebra, but Egyptian algebra was way more basic compared to the Babylonians. The Egyptians mostly stuck with linear equations. You know, the simple stuff like x plus 3 equals 7. There's this document called the Rhind Papyrus, written around 1650 BCE by a guy named Ahmes. He copied it from an even older text that dated back to somewhere between 2000 and 1800 BCE. The Rhine Papyrus is basically an ancient math textbook. It's full of problems, and it shows us exactly how the Egyptians thought about equations. They used a term that translates to aha, or heap, for the unknown quantity. So instead of writing x plus x times a equals b, they'd write it all out in words, referring to the heap and its parts. The Egyptians had this technique called the method of false position. Basically, you'd make a guess, work through the problem with that guess, see how far off you were, and then adjust proportionally to get the right answer. It's not elegant, but it works. And sometimes that's all you need. Now, let's jump forward to ancient Greece. This is where things get interesting in a different way. The Greeks are famous for geometry, right? Euclid, Pythagoras, all those guys. But they also did algebra, just not in the way you'd expect. The Greeks practiced what's called geometric algebra. Instead of using numbers and equations, they thought about everything in terms of shapes and areas. To solve what we'd call an algebraic equation, they draw diagrams and use properties of geometric figures. Euclid's Elements, which is basically the geometry textbook that ruled for 2,000 years, actually contains a lot of algebraic ideas. They're just all expressed geometrically. But then there's Diophantus. Oh man, Diophantus is a trip. This guy lived around 250 CE in Alexandria, and he wrote this work called Arithmetica. Originally, it was 13 books, but only 10 have survived, 6 in Greek and 4 in an Arabic translation that was discovered in 1968. Diophantus is sometimes called the father of algebra, though that's controversial. Here's what makes him special. He was one of the first people to use symbols in mathematics. Not the symbols we use today, but symbols nonetheless. He had a symbol for the unknown quantity, symbols for powers of that unknown, symbols for operations. It was syncopated algebra, somewhere between writing everything out in words and using full symbolic notation. The problems in Arithmetica are fascinating. Diophantus would set up equations, often what we call indeterminate equations, meaning they have more than one solution, and then he'd work through them step by step. He'd show you how to find rational number solutions to these problems. And the thing is, his methods were genuinely clever. He'd make substitutions, manipulate equations, use techniques that still work today. But here's the kicker. We don't even know exactly when Diophantus lived. The best guess is somewhere around 250 CE, but that could be off by a century in either direction. There's this famous mathematical riddle that's supposed to describe his life. It's called Diophantus's epitaph. It goes something like: a sixth of his life was childhood, a 12th was youth, then a 7th passed before he got married. 5 years later, he had a son. His son lived to half his father's age, and Diophantus lived 4 more years after his son died. If you solve it, which is itself an algebraic problem, you get that Diophantus lived to be 84. But nobody knows if this is actually true or just a clever math puzzle someone made up later. What we do know is that Diophantus had a huge influence on later mathematics. His work was studied in the Greek-speaking world for centuries after his death. A philosopher named Hypatia, who lived in Alexandria in the 4th and 5th centuries, wrote a commentary on Arithmetica. And when Arabic scholars started translating Greek mathematical texts, Diophantus's work was one of the big ones. Now, let's talk about India, because while all this is happening in the Mediterranean and Middle East, some absolutely groundbreaking stuff is going on in the Indian subcontinent. Indian mathematics has a long and rich history. There's evidence of sophisticated mathematical thinking going back to ancient times. But things really take off during what's called the classical period, from around 400 to 1200 CE. One of the big names from this era is Brahmagupta. This guy was born in 598 CE in what's now Rajasthan, India, and he became the head of the astronomical observatory at Ujjain, which was like the mathematical center of India at the time. Brahmagupta wrote this massive work called the Brahmasfuta Siddhanta in 628 CE. It's an astronomical text, but it includes extensive sections on mathematics. And this is where things get really interesting. First off, Brahmagupta gave us rules for working with zero. Now, zero as a concept had been around for a while. The Babylonians used it as a placeholder, and Indian mathematicians had been developing the idea. But Brahmagupta was one of the first to really treat zero as a number you could calculate with. He gave rules like 1 plus 0 equals 1, 1 minus 0 equals 1, 1 times 0 equals 0. He even tried to tackle division by 0, though he got that one wrong. He said that 1 divided by 0 equals 0, which we now know doesn't work. It would be another few hundred years before anyone figured out that dividing by 0 is undefined, but still, the fact that he was thinking about it at all was a big step. But here's what's really groundbreaking. Brahmagupta worked with negative numbers. Before this, most mathematicians didn't accept the idea of negative quantities. How can you have negative 5 apples? It doesn't make physical sense, right? But Brahmagupta saw that mathematically you could treat negative numbers as legitimate values. He called them debts as opposed to property, and he figured out the rules for calculating with them. He knew that a negative times a negative gives you a positive. He knew that a negative times a positive gives you a negative. These might seem obvious to us now, but remember, nobody had formalized this before. This was revolutionary thinking. Brahmagupta also used symbols in his work, though differently than Diophantus. He used abbreviations and different symbols for different powers. He even used the initials of color names to represent different unknown quantities, like the black unknown or the blue unknown, which is a pretty creative way to handle multiple variables. He solved linear equations, quadratic equations, and even tackled what we now call Pell's equation, which is a type of Diophantine equation. His work on this was so advanced that it wouldn't be matched in Europe for over 1,000 years. Then, a few centuries later, we get Bhaskara too. He lived from 1114 to about 1185, and he took Indian mathematics to new heights. Bhaskara was also based at Ujjain. It was clearly the place to be if you were a mathematician in medieval India. Bhaskara wrote several important works, including the Lilavati and the Bijaganita. The Lilavati focuses on arithmetic and includes lots of practical problems. The Bijaganita is all about algebra. The word literally means seed counting or root extraction. Bhaskara gave general solutions to various types of equations. He worked extensively with indeterminate equations. He explored problems involving Pythagorean triples, and like Brahmagupta before him, he tried to deal with division by zero. He came up with this idea that a quantity divided by zero becomes infinite, which is closer to our modern understanding, but still not quite right. What's really cool about Indian mathematical texts is how they were written. They used Sanskrit verse with a very compact, poetic style. The sutras, these mathematical rules, were deliberately short and sometimes even ambiguous. The idea was that students would memorize them and then work through examples with a teacher who would explain all the details. This tradition of mathematical scholarship in India had a massive influence on the rest of the world. When Arabic scholars started learning about Indian mathematics, they incorporated these ideas into their own work. And that brings us to the Islamic Golden Age. We need to talk about Al-Khwarizmi. This is huge. Muhammad ibn Musa al-Khwarizmi lived in the 8th and 9th centuries in Baghdad, which was the intellectual capital of the world at that time. The city was a melting pot of ideas, Greek, Indian, Persian, and Arabic knowledge, all coming together. Around 820 CE, Al-Khwarizmi wrote a book with a really long Arabic title that translates roughly to the compendious book on calculation by completion and balancing. The key words here are Algebra and Al-Muqabala. These refer to operations you do on equations. Algebra, which is where we get the word algebra, means something like restoration or completion. It refers to moving negative terms to the other side of an equation. So, if you have x minus 3 equals 5, you'd restore by adding 3 to both sides to get x equals 8. Al-Muqabala means balancing. It's about canceling like terms on opposite sides of an equation. If you have x plus 5 equals x plus 8, you'd balance by subtracting x from both sides. Now, Al-Khwarizmi didn't invent these techniques. People had been manipulating equations for centuries, but he systematized them. He created a methodical approach to solving equations that anyone could follow, and that's what made his book revolutionary. The book is organized around 6 standard types of equations. Remember, at this time, people didn't accept negative numbers or zero as coefficients, so you had to consider different cases separately. Al-Khwarizmi worked through linear equations and quadratic equations, showing step by step how to solve each type. And here's the thing. This wasn't abstract mathematics for its own sake. Al-Khwarizmi wrote this book because people needed it for practical reasons. How do you divide an inheritance among family members according to Islamic law? How do you calculate land areas? How do you figure out business partnerships and debts? Algebra was a tool that made these calculations possible and consistent. Al-Khwarizmi's book was translated into Latin in the 12th century by guys like Robert of Chester and Gerard of Cremona. When Europeans got their hands on these translations, it blew their minds. This systematic approach to solving equations was unlike anything they'd seen before. In fact, the Latin translation of Al-Khwarizmi's name, algorithmi, became our word, algorithm. That's right. Every time you use that word, you're referencing this 9th century Persian mathematician. After Al-Khwarizmi, Islamic mathematics continued to flourish. Scholars like Al-Karaji, Omar Khayyam, yes, the poet, and others made significant contributions. They expanded on Diophantus's work, incorporated Indian techniques, and pushed algebra to new levels of sophistication. Omar Khayyam, who lived in the 11th and 12th centuries, worked on cubic equations, equations involving x cubed. He couldn't solve them algebraically, but he found geometric solutions using conic sections. He also wrote about the theoretical foundations of algebra as a discipline. Meanwhile, Chinese mathematicians were also doing amazing work. There's this text called The 9 Chapters on the Mathematical Art, compiled over hundreds of years from around the 10th century BCE to the 2nd century CE. It contains methods for solving systems of linear equations that look remarkably similar to what we call Gaussian elimination today, except it predates Gauss by over 1500 years. Chinese mathematicians developed matrix-like constructs for solving these systems. They worked with polynomial equations using something called Horner's method, which again was discovered independently in Europe much later. There's this beautiful recursive approach to mathematics in the Chinese tradition that's quite different from the Greek geometric approach or the Arabic algebraic approach. So by the time we get to the European Renaissance, all of this knowledge is starting to flow together. Greek texts are being rediscovered, Arabic mathematics is being translated, and European mathematicians are hungry for new ideas. Enter Fibonacci. Leonardo Fibonacci from Pisa traveled around North Africa and the Middle East in the late 12th and early 13th centuries. He learned about Arabic numerals, the number system we use today, and about algebra. In 1202, he published the Liber Abac, which introduced Arabic numerals and algebraic techniques to Europe. The title literally means Book of Calculation, and it's full of practical problems solved using the new methods. Fibonacci showed European merchants and scholars that this Arabic Indian number system was way better than Roman numerals for doing calculations, and he demonstrated how algebra could solve real-world problems. But it would be another few hundred years before European mathematicians made their next big breakthrough. And when they did, it involved one of the juiciest dramas in the history of mathematics. We're talking about the cubic equation. For centuries, mathematicians had been able to solve linear equations that's first degree, like x plus 3 equals 7. They could solve quadratic equations, second degree, like x squared plus 3x plus 2 equals 0. The quadratic formula, or variations of it, had been known since ancient times. But cubic equations, third degree, involving x cubed, were a different beast entirely. Nobody could find a general solution. It was one of the great unsolved problems of mathematics. In the early 1500s, in Bologna, Italy, there was this mathematician named Scipione del Ferro. He was a professor at the University of Bologna, and around 1515, he figured out how to solve one type of cubic equation, specifically equations that look like x cubed plus mx equals n. But here's the thing about academic life in Renaissance Italy. Your job security depended on your reputation. and your reputation depended on winning public mathematical competitions. These were like intellectual duels, where mathematicians would challenge each other to solve problems. If you could solve problems that your opponent couldn't, you'd win prestige, students, and better positions. So Del Ferro kept his solution secret. He only told a few trusted students, including a guy named Antonio Fior. Del Ferro died in 1526, and Fior thought, now I've got this secret weapon. I can challenge anyone to a mathematical duel and win. In 1535, Fior challenged a mathematician named Niccolo Fontana to a competition. Fontana was better known as Tartaglia, the stammerer, because of a speech impediment he'd had since childhood. Fior figured he'd easily beat Tartaglia because he had Del Ferro's secret method. But Tartaglia was brilliant. When he saw the types of problems Fior was posing, he realized there must be a general method. And in an intense period right before the competition, Tartaglia figured it out. He discovered how to solve cubic equations independently. When the competition happened, Tartaglia crushed Fior. He solved all of Fior's problems while Fior couldn't solve any of Tartaglia's. It was a total rout, and Tartaglia became famous. Now enter Girolamo Cardano. Cardano was this Renaissance man, a doctor, mathematician, astrologer, philosopher, and general eccentric. He was writing a comprehensive book on mathematics, and he wanted to include Tartaglia's method for solving cubics. Cardano started courting Tartaglia, flattering him, promising to introduce him to important people. Finally, in 1539, Tartaglia agreed to share his method with Cardano, but only under a solemn oath that Cardano wouldn't publish it until Tartaglia had published it first. Tartaglia even wrote out the solution as a poem, trying to make it harder for others to steal. The poem gave the steps in verse form, all cryptic and hard to follow if you didn't already kind of know what it was talking about. Cardano worked on the problem for years. Along with his brilliant student, Lodovico Ferrari, he extended Tartaglia's method to handle all types of cubic equations. And Ferrari, using similar techniques, figured out how to solve quartic equations, fourth-degree equations with x to the fourth power. But they couldn't publish because of Cardano's oath to Tartaglia. Then, in 1542, Cardano and Ferrari traveled to Bologna. There, they discovered that Del Ferro's nephew had notebooks showing that Del Ferro had discovered the solution to cubics before Tartaglia, back around 1515. Cardano figured this got him off the hook. He wasn't publishing Tartaglia's work, he was publishing Del Ferro's work, which Tartaglia had discovered independently. So, in 1545, Cardano published the Ars Magna, the Great Art. This book was a bombshell. It contained the solutions to cubic and quartic equations, along with a ton of other algebra. Cardano gave full credit to both Del Ferro and Tartaglia for the cubic, and to Ferrari for the quartic. It was one of the most important mathematical works of the Renaissance. Tartaglia was furious. He felt completely betrayed. He accused Cardano of breaking his sacred oath. He published pamphlets attacking Cardano's character and mathematical ability. Cardano mostly stayed quiet, but Ferrari jumped into the fray, defending his teacher. Ferrari and Tartaglia exchanged a series of increasingly hostile pamphlets. We're talking serious trash talk in Renaissance Italian mathematical style. Finally, Ferrari challenged Tartaglia to a public mathematical debate. Tartaglia eventually accepted, thinking he could easily beat this young upstart. The debate was scheduled for August 10, 1548, in Milan, but it became clear on the first day that Ferrari had a much deeper understanding of the new algebra than Tartaglia did. Ferrari had worked extensively with Cardano on extending and generalizing these methods. He could handle questions that Tartaglia couldn't. That night, Tartaglia slipped out of Milan and fled. He never showed up for the second day of the debate. Ferrari won by default. Tartaglia's reputation was destroyed. He died penniless and largely forgotten in 1557. Meanwhile, Cardano became recognized as the greatest mathematician in Europe. The Ars Magna is still considered one of the three greatest scientific works of the early Renaissance, alongside Copernicus's book on planetary motion and Vesalius's anatomy text. But here's what's mathematically interesting. In solving cubic equations, Cardano and Ferrari encountered something weird. Sometimes their formulas required taking the square root of negative numbers. This didn't make sense to them. You can't have a negative area or a negative square. But the formula seemed to work anyway if you just manipulated these impossible numbers algebraically. This was the beginning of complex numbers. Cardano mentioned them in the Ars Magna, but he didn't really understand what they meant. It would be another mathematician, Raphael Bombelli, who worked all this out a few decades later. Bombelli realized that you could treat the square root of -1 as a legitimate mathematical object. We now call it I, the imaginary unit. And if you work with numbers of the form a plus bi, where a and b are real numbers, and I is the square root of -1, you get the complex numbers. These turned out to be incredibly important, not just for algebra, but for physics, engineering, everything. Now, we need to talk about the next big revolution in algebra, symbolic notation, because even though people could solve cubic and quartic equations, the notation was still clunky. Mathematicians still wrote things out in ways that were hard to follow and hard to generalize. Enter François Viette. Viette was a French lawyer who did mathematics on the side. In 1591, he published a work called In Artem Analyticam Isagoge, Introduction to the Analytic Art. What Viette did was revolutionary. He proposed using letters to represent not just unknown quantities, but also known quantities, parameters. He used vowels for unknowns and consonants for knowns. So, instead of working with specific numbers, you could write general formulas that worked for any numbers. This is huge. This is the birth of symbolic algebra. Instead of solving a specific equation like x squared plus 6x plus 8 equals 0, you could work with the general quadratic a squared plus b times a equals z and develop methods that work for all quadratics. Viette still had some limitations. He was stuck in the geometric mindset in some ways. He required equations to be homogeneous, meaning all terms had to have the same dimensional power. This was a vestige of thinking about algebra geometrically, where you couldn't add a length to an area because they're different types of things. But the key insight was there. You could manipulate symbols according to rules, and those symbols could represent any numbers. This made algebra vastly more powerful. Then came René Descartes. In 1637, Descartes published La Géométrie as an appendix to his philosophical work Discourse on Method. This book changed everything. Descartes took Vièt's symbolic algebra and perfected it. He introduced the notation we still use today: X, Y, and Z for unknowns, A, B, and C for knowns. He used superscripts for exponents, x squared, x cubed, and so on. He got rid of the homogeneity requirement, allowing you to add terms with different powers. But more importantly, Descartes connected algebra and geometry in a fundamental way. He showed that you could describe geometric curves using algebraic equations, and you could solve geometric problems using algebra. This is what we now call analytic geometry or coordinate geometry. The idea is brilliant in its simplicity. Take two perpendicular lines, axes. Every point in the plane can be described by two numbers, coordinates. A curve is just a set of all points whose coordinates satisfy some equation. A circle centered at the origin with radius r is all the points where x squared plus y squared equals r squared. A parabola is y equals x squared, and so on. This fusion of algebra and geometry was transformative. It meant you could attack geometric problems with algebraic tools, and vice versa. It opened up entirely new areas of mathematics. And it set the stage for calculus, which Newton and Leibniz would develop later in the 17th century. By the 18th century, algebra was becoming more and more powerful. Mathematicians could solve incredibly complex equations, manipulate symbols with great facility, and apply algebra to problems in physics, astronomy, and engineering. But there was still this nagging question: what about quintic equations? Fifth-degree equations with x to the fifth power. People had figured out linear equations thousands of years ago. Quadratics were ancient. Cubics and quartics were solved in the Renaissance. Surely someone could solve quintics, right? Mathematicians tried for centuries. The great Leonhard Euler worked on it. Joseph Louis Lagrange made important progress in understanding why the lower degree equations could be solved. He developed this method called Lagrange resolvents, where he studied equations by looking at how their roots could be permuted. This was a key insight. Lagrange realized that solving an equation was connected to understanding the symmetries of its roots, how you could rearrange them, but his method didn't extend to quintics. In the late 18th century, an Italian mathematician named Paolo Ruffini claimed to prove that quintics couldn't be solved by radicals, meaning there's no general formula using only addition, subtraction, multiplication, division, and roots. But his proof had some gaps, and people didn't fully accept it. Then, in 1824, a young Norwegian mathematician named Niels Henrik Abel published a rigorous proof that the general quintic equation cannot be solved by radicals. This was shocking. For the first time, mathematics had proven that something was impossible. Not just difficult, actually impossible. Abel's proof was beautiful, but it didn't explain why some specific quintics could be solved. For example, x to the fifth minus 1 equals 0 can be solved. So could x to the fifth minus x equals 0. Why do these work but not the general case? This is where Évariste Galois comes in. And Galois' story is one of the most tragic in mathematics. Galois was born in 1811 near Paris. He was a mathematical prodigy, but also hot-headed and politically radical. He tried twice to get into the École Polytechnique, the top school in France, but failed both times, probably because he was so far ahead of the examiners that he couldn't explain his thinking in ways they understood. At 17, Galois submitted a paper on solving equations to the French Academy of Sciences. The mathematician reviewing it was Augustin Louis Cauchy, who suggested Galois expand it and resubmit. Galois did, but the new reviewer, Joseph Fourier, died before reading it. The manuscript was lost. Galois submitted another paper in 1830, but it was rejected as too obscure and poorly written. Throughout all this, Galois was getting more involved in radical republican politics. He was arrested multiple times for political activities. In 1832, at the age of 20, Galois was challenged to a duel. The circumstances are murky. It might have been over a woman, or it might have been a political setup, but Galois knew he was likely to die. The night before the duel, he stayed up writing a letter to his friend, Auguste Chevalier, frantically outlining his mathematical ideas. He covered page after page with theorems, proofs, and notes about what he'd discovered. In the margin, he kept writing, "I have not time." There was so much he wanted to say, and so little time left. The next morning, Galois was shot in the duel. He died the following day from his wounds. What Galois had discovered and what he tried to communicate in that final letter was the connection between group theory and the solvability of equations. He showed that you could associate a group, a collection of permutations of the roots with any polynomial equation, whether or not that equation could be solved by radicals depended on the structure of this group. If the group had a certain property, being solvable in the group theory sense, then the equation could be solved by radicals. If not, it couldn't. Quintic equations generally have groups that aren't solvable, which is why they can't be solved in general. This was the birth of Galois theory, and it was revolutionary. Galois had created an entirely new way of thinking about algebra. Instead of focusing on manipulating equations and finding solutions, he focused on the abstract structure, the symmetries underlying those equations. But here's the tragedy. Galois' work was so far ahead of its time that mathematicians couldn't understand it for years. When his papers were finally published in 1846, 14 years after his death, people struggled to make sense of them. It took decades for mathematicians to fully grasp what Galois had done. Joseph Liouville, who published Galois' work, completely missed the group theoretic core. It wasn't until Camille Jordan wrote his Traité des substitutions et des équations algébriques in 1870 that Galois theory started to be properly understood and appreciated. By the late 19th century, mathematicians were starting to think about algebra in completely new ways. Instead of just solving equations, they were studying abstract structures, groups, rings, fields. A group is a set with an operation that satisfies certain rules. The integers, under addition, form a group. Non-zero rational numbers, under multiplication, form a group. Symmetries of geometric objects form groups. Once you abstract the concept, you realize groups show up everywhere in mathematics. A ring is a set with two operations, like addition and multiplication, that satisfy certain rules. The integers form a ring, polynomials form a ring, matrices form a ring. A field is a ring where you can also divide, like the rational numbers, real numbers, or complex numbers. This abstraction was powerful because once you proved something about groups in general, it applied to all specific groups. You could understand the common structure underlying seemingly different mathematical objects. The German mathematician Richard Dedekind was one of the pioneers of this abstract approach. He worked on algebraic number theory and made rigorous definitions of many concepts that had been used intuitively before. David Hilbert took this even further. In the late 19th and early 20th centuries, Hilbert revolutionized algebra by focusing on abstract structures and their properties rather than on computational techniques. Emmy Noether, working in the early 20th century, became one of the most influential figures in abstract algebra. Despite facing discrimination as a woman in mathematics, she had to lecture under Hilbert's name at first because the university wouldn't officially hire a female professor. She made groundbreaking contributions to ring theory and the general theory of ideals. Noether proved theorems that unified and generalized huge swaths of earlier work. Her approach was to identify the essential abstract properties that made theorems work, then prove things at that level of generality. This Noetherian approach, as it came to be called, became the standard way of doing modern algebra. By the mid-20th century, a group of mathematicians writing under the collective pseudonym Nicolas Bourbaki set out to reorganize all of mathematics on a rigorous axiomatic foundation. Their approach, though sometimes criticized as overly abstract, emphasized the structural unity of mathematics. Abstract algebra became the study of these structures, groups, rings, fields, modules, vector spaces, algebras, and more, for their own sake, exploring their properties and relationships. It became less about solving specific equations and more about understanding the abstract patterns that equations exemplify. Linear algebra emerged as a major field in its own right. This is the study of vector spaces and linear transformations, things that can be represented by matrices. Linear algebra turns out to be incredibly useful in physics, computer science, statistics, and just about every branch of applied mathematics. In the 20th century, algebra found applications that ancient mathematicians never could have imagined. Abstract algebra is used in cryptography, the mathematics of codes and secure communication. Every time you send a secure message over the internet, you're relying on algebra, particularly number theory and group theory. Algebra is used in error-correcting codes, which make it possible to transmit data reliably even when there's noise in the channel. Your CD player uses algebra to reconstruct music even when there are scratches on the disc. Quantum mechanics uses the algebra of Hilbert spaces and operator algebras. String theory uses sophisticated algebraic geometry. Computer science uses Boolean algebra and other algebraic structures, and mathematicians keep discovering new connections. In the 1960s through 1980s, a massive collaborative effort resulted in the classification of finite simple groups. This was a huge undertaking. The proof spans over 10,000 journal pages written by hundreds of mathematicians. It catalogs all the basic building blocks from which all finite groups can be constructed. Category theory, developed in the mid-20th century, provides an even more abstract framework for understanding mathematical structures. Categories let you talk about the relationships between different kinds of mathematical objects in a very general way. So where are we now? Algebra in the 21st century is a vast, sprawling field with connections to almost every other area of mathematics. Pure algebraists study structures that may seem incredibly abstract, things like non-commutative rings, algebraic topology, homological algebra, representation theory. But these abstract ideas keep finding unexpected applications. Topology, the study of shapes and spaces, uses heavy doses of algebra. Number theory, which seems like the purest of pure math, turns out to be crucial for cryptography. Algebraic geometry provides tools for studying everything from particle physics to machine learning. And we're still discovering new things. The Langlands program, one of the biggest projects in modern mathematics, is trying to unify different areas of mathematics through deep connections involving algebra, number theory, and geometry. Andrew Wiles' proof of Fermat's last theorem in 1994, solving a problem that had been open for over 350 years, relied heavily on modern algebraic techniques. When you step back and look at the whole history, it's kind of amazing. We started with Babylonians writing word problems on clay tablets, trying to divide land and calculate loans. We moved through Egyptian false position methods, Greek geometric algebra, Diophantus' syncopated notation. We saw Indian mathematicians grappling with negative numbers and zero Islamic scholars systematizing equation solving, Chinese mathematicians developing matrix methods. Renaissance Italians had literal duels over cubic equations. Viet and Descartes created symbolic algebra. Galois died at 20 after revolutionizing mathematics the night before a duel. And now we have this incredibly rich, abstract, powerful subject that touches almost every part of modern life. When you use your phone, algebra is handling the encryption. When you watch a video, algebra is compressing and error-correcting the data. When physicists try to understand the universe, they're using algebraic structures. But here's what I find most beautiful. Algebra, at its core, is about finding patterns and structure. It's about taking specific problems and asking, what's the general principle here? What's the underlying structure that makes this work? That impulse to abstract, to generalize, to find a common thread, that's the same impulse that drove Al-Khwarizmi to systematize equation solving, that drove Galois to see groups lurking behind equations, that drives modern algebraists to study structures that seem far removed from any practical application but end up being useful in ways nobody predicted. The history of algebra shows us that mathematics isn't just about answers. It's about understanding why the answers work. It's about building frameworks that let us solve not just one problem, but whole classes of problems we haven't even thought of yet. When Brahmagupta worked out the rules for negative numbers, he wasn't thinking about quantum mechanics or signal processing. When Galois developed group theory, he wasn't thinking about cryptography or particle physics. But the structures they discovered turned out to describe fundamental aspects of reality and to enable technologies they never could have imagined. And that's the thing about algebra. Every generation thinks they've figured it out, that they've reached the end of what there is to discover. The Babylonians had their methods. The Greeks had their geometric algebra. Renaissance mathematicians had symbolic algebra and could solve cubics and quartics. But then someone comes along and shows there's another level, another layer of abstraction, another way of seeing the patterns. Galois saw groups where others saw only equations. Noether saw ideals where others saw only specific polynomial rings. Category theorists saw functors where others saw only mappings between structures. And each new level of abstraction, far from making mathematics more obscure, actually makes it more powerful. Because when you understand the deep structure, you can apply it to situations that superficially seem completely different. The same group theory that explains why you can't solve quintic equations also explains symmetries in crystals, particle physics, and musical harmony. This same linear algebra that started as a method for solving systems of equations now underlies computer graphics, machine learning, and quantum computing. So what's next? Where is algebra going in the 21st century and beyond? Nobody knows for sure, but there are some exciting directions. Computational algebra is getting more sophisticated. We can now solve algebraic problems using computers that would have been unthinkable to tackle by hand. This lets mathematicians explore and conjecture in new ways. Connections with computer science are growing stronger. Ideas from algebra are helping design better algorithms, understand complexity, and develop new programming paradigms. Quantum computing might revolutionize how we think about computation and algebra. Quantum algorithms exploit algebraic structures in ways that classical computers can't match, and mathematicians are still finding new structures to study. Hopf algebras, quantum groups, vertex algebras. These are relatively recent inventions that are opening up new areas of research. But beyond specific results or applications, the spirit of algebra continues. It's the spirit of seeing past the surface details to the underlying structure, of asking not just what is the answer, but why does this work and what's the general principle. Every time you solve for x in a simple equation, you're participating in a tradition that goes back thousands of years. You're using methods that were developed by people across different continents, different cultures, different eras, all driven by the same curiosity about how to manipulate unknowns, how to find patterns, how to understand structure. The Babylonian calculating on a clay tablet, the Indian mathematician working with colored unknowns, the Islamic scholar restoring and balancing, the Renaissance Italian guarding his secret method, the French revolutionary writing frantically on his last night of life, the German professors building axiomatic systems. They're all part of the same story, and that story isn't over. We're still writing it. Every new theorem, every new connection discovered, every new application found, it's all adding to this magnificent edifice that we call algebra. So the next time you're working through an algebraic equation, maybe take a moment to appreciate the journey that X you're solving for. It represents centuries of human thought. The operations you're using, they were developed and refined by some of the brightest minds in history. The notation you take for granted, people literally died arguing about who discovered it first. Algebra isn't just a set of techniques for manipulating symbols. It's a way of thinking about the world. It's a language for describing structure and pattern. It's a testament to human ingenuity and our endless quest to understand the universe through abstraction and reason. From clay tablets to quantum computers, from word problems to abstract category theory, algebra has been on an incredible journey. And the most exciting part, the journey is far from over. We are still discovering, still abstracting, still finding new structures and new connections, because that's what algebra is really about. Not memorizing formulas or grinding through homework problems, though, yeah, you have to do that stuff too. But at its heart, algebra is about seeing the patterns that connect everything. It's about taking the specific and finding the universal. It's about pushing past what seems impossible and discovering that with the right framework, the right abstraction, the right structure, you can understand things that seemed incomprehensible before. And maybe that's the most important lesson from the history of algebra. The problems that seem impossible today might have solutions tomorrow, but those solutions might require thinking in ways we haven't imagined yet. They might require new structures, new abstractions, new ways of seeing. Galois couldn't solve the quintic equation the way people wanted, but he solved a deeper problem. He explained why some equations could be solved and others couldn't by revealing the group structure underneath. That's more powerful than any specific solution could ever be. So when you're stuck on an algebra problem, remember, you're in good company. Mathematicians have been getting stuck for thousands of years, but they kept pushing, kept abstracting, kept looking for the deeper structure. And slowly, impossibly, we've built this incredible framework for understanding not just numbers and equations, but structure itself. That's the story of algebra. From ancient Babylonian merchants to modern theoretical physicists, it's been a long, strange, beautiful trip, and we're still just getting started. Let's dive deeper into some of these stories, because there's so much fascinating detail we've only scratched the surface of. Let's talk more about what daily life was like for these mathematicians, what actually motivated their work, and some of the wild details that textbooks usually skip over. Starting with Babylon again, because honestly, what the Babylonians accomplished is mind-blowing when you think about what tools they had available. These people didn't have calculators. They didn't have paper. They didn't even have a symbol for zero initially, though they developed one later as a placeholder. They worked with a sexagesimal system, base 60, which is why we still have 60 seconds in a minute and 60 minutes in an hour. Think about doing multiplication in base 60. It's complicated, but they created extensive multiplication tables on clay tablets to help with calculations. And these weren't just mathematical exercises for fun. The Babylonians needed this stuff. They had a complex economy with contracts, loans, and interest rates. They needed to calculate compound interest, which is essentially solving exponential equations. They had to divide estates among heirs according to elaborate rules. They had agricultural problems. How much grain do you need to plant this much land? How much will it yield? One clay tablet, we have thousands of these things, contains a problem about renting a bull. How much does it cost to rent a bull for plowing? How do you split the cost among multiple farmers? How do you calculate depreciation? These are algebraic problems dressed up in everyday language. The Babylonians developed this flexible system where they could set up equations, manipulate them to eliminate fractions, and solve for unknowns. They understood that if two things are equal, you can do the same operation to both sides and maintain equality. That's the foundation of algebra right there, and they had it nearly 4,000 years ago. What's also fascinating is how this knowledge was transmitted. Scribes would copy these tablets, learning the methods by reproducing the examples. There were what we'd call textbooks, tablets with series of increasingly complex problems, clearly designed for teaching. And the Babylonians weren't just following rote procedures. Some of these problems show genuine mathematical creativity. They'd set up problems in clever ways, use substitutions to simplify equations, develop algorithms that we'd recognize today as quite sophisticated. When you look at Egyptian mathematics, it's a different vibe. The Egyptians were incredibly practical. The Rhind papyrus starts with Ahmes saying he's going to give a thorough study of all things, insight into all that exists, knowledge of all obscure secrets. Bold claim for a math textbook, but then it delivers. There are problems about distributing bread among workers in different ratios, problems about calculating the slope of a pyramid's face, which they called the second, problems about calculating areas and volumes, and yes, algebra problems. The method of false position is actually pretty clever when you think about it. Say you want to solve x plus x divided by 7 equals 19. You make a guess, let's say x equals 7, because that makes the fraction easy. Well, 7 plus 7 divided by 7 equals 7 plus 1 equals 8. That's not 19, it's off by 11. But here's the trick. If you guessed 7 and got 8 and you need 19, then you need to scale everything up. 19 divided by 8 is about 2.375. So multiply your guess by that ratio. 7 times 2.375 gives you 16.625. And if you check 16.625 plus 16.625 divided by 7 actually does equal about 19. It's not as slick as using algebra directly, but it works. And for practical problems where you just need a good enough answer, it's actually pretty efficient. The Egyptians also had this beautiful notation for fractions. They could write any fraction as a sum of unit fractions, fractions with 1 in the numerator. So instead of writing 2/3, they might write 1/2 plus 1/6. They had special symbols for these common fractions. This seems weird to us, but it worked for them. They had tables of these decompositions, and scribes would memorize the common ones. It was just a different way of thinking about parts of wholes. Now, Greek mathematics is interesting because the Greeks were almost allergic to algebra in the form we know it. They had this deep philosophical commitment to geometry as the purest form of mathematics. Numbers to the Greeks were for counting discrete objects or measuring geometric quantities. The Pythagoreans, followers of Pythagoras, thought that all of reality could be understood through whole numbers and their ratios. They believed in the mystical properties of numbers. And then one of them discovered that the square root of 2 is irrational. It can be expressed as a ratio of whole numbers. Legend has it that this was so disturbing to the Pythagorean worldview that they tried to keep it secret. The guy who revealed it was supposedly thrown off a boat and drowned. That's probably not true, but it shows how seriously the Greeks took their mathematical philosophy. So when Greeks did what we'd call algebra, they did it geometrically. Euclid's Elements, Book 2, is full of algebraic identities expressed as geometric propositions. The identity we write as a plus b squared equals a squared plus 2ab plus b squared is presented as a theorem about areas of squares and rectangles. You draw a square with side length a plus b. You can partition it into a square with side length a square with side length b, and two rectangles with sides a and b. Add up their areas and you get the identity. It's algebra, but it's geometric algebra. This approach had advantages. It was rigorous and grounded in geometric intuition, but it also had limitations. It's hard to work with higher powers, hard to generalize, hard to manipulate the way you can with symbolic algebra. Enter Diophantus, who was doing something different. He wasn't doing geometry. He was solving numerical problems, but using general techniques. He had notation, crude by our standards, but notation nonetheless. Here's the thing about Arithmetica that makes it so interesting. Diophantus was clearly brilliant at finding clever solutions to hard problems. He'd see patterns, make substitutions, use tricks that would simplify equations, but he didn't present his work as a systematic method. It was more like, here's a problem, watch me solve it using this clever trick. Reading Diophantus is like watching a master craftsman at work. You can see that he knows what he's doing, but he's not necessarily explaining his thought process. Later mathematicians had to reverse engineer his methods from the examples he gave, and some of his problems are genuinely difficult. He'd set up indeterminate equations with multiple unknowns, but fewer equations than unknowns, so they have infinitely many solutions. Then he'd add conditions to narrow it down. Find positive rational solutions. Find solutions where certain expressions are perfect squares. This is hard stuff. Even today, solving Diophantine equations where you're looking for integer or rational solutions, is a major area of number theory. There is no general method that works for all of them. Some are easy, some are impossible, and figuring out which is often the hard part. Fermat, yes, that Fermat of Fermat's last theorem, was obsessed with Diophantus. He owned a copy of Arithmetica, and he'd write notes in the margins about what he discovered. Most famously, next to a problem about Pythagorean triples, he wrote that he'd found a proof that the equation x to the n plus y to the n equals z to the n has no integer solutions for n greater than 2, but the margin was too small to contain the proof. That margin note led to 350 years of mathematical effort trying to prove or disprove Fermat's last theorem. It wasn't settled until Andrew Wiles proved it in 1994 using sophisticated techniques from modern algebraic geometry that Fermat definitely didn't have access to. So either Fermat was mistaken about having a proof, or he had some clever elementary proof that we've never found. Most mathematicians think he was mistaken, but we'll never know for sure. Moving to India, the mathematical tradition there was really something special. Indian mathematics developed somewhat independently, though there was definitely some cross-pollination with Greece and later with Islamic mathematics. The Indian approach was algorithmic. They'd state rules, sutras, in very compressed verse form. Then they'd work through examples showing how to apply the rules. The emphasis was on computation and problem solving. Aryabhata, who lived in the late 5th and early 6th centuries, wrote the Aryabhatiya when he was 23 years old. This work covers arithmetic, algebra, trigonometry, and astronomy. He gave approximations for pi, methods for finding square roots and cube roots, and solutions to linear and quadratic equations. He also stated that the Earth rotates on its axis, which was a radical idea at the time. Most people thought the Earth was stationary and the stars rotated around it. Aryabhata said, no, the Earth spins, and that's why the stars seem to move. He was right, but this view wasn't accepted by everyone, even in India. Brahmagupta came about a century after Aryabhata, and he was critical of some of Aryabhata's astronomical views. Medieval Indian mathematicians didn't just accept everything from previous generations. They argued, debated, tried to improve on earlier work. The thing about negative numbers is interesting because it shows how mathematical concepts that seem obvious once you understand them were once deeply controversial. How can you have -5 sheep? You can't. But you can have a debt of 5 sheep. You owe 5 sheep. Brahmagupta framed it in terms of property and debt, which made it concrete. Positive numbers are property, things you own. Negative numbers are debts, things you owe. When you add property and property, you get more property. When you add debt and debt, you get more debt. When you add property and debt, they partially cancel out. This framing made the rules for computing with negatives make sense. A negative times a positive is negative. Debt times property is debt. A negative times a negative is positive. When you multiply two debts, you get property. That last one is less intuitive, but if you work through examples, it makes sense. The Indian mathematicians also worked extensively with what they called kutaka, methods for solving linear Diophantine equations. These are equations like ax plus by equals c, where you're looking for integer solutions. These problems come up in astronomy, calculating when celestial events will recur, and in everyday life, dividing goods in certain ratios. Bhaskara Tus Lilavati is written as if the problems are being posed to a woman named Lilavati, who might have been his daughter. Some of the problems are quite charming. Out of a swarm of bees, 1/5 part settled on a blossom of Kadamba, 1/3 on a flower of Silindara. 3 times the difference of those numbers flew to a bloom of Krutaja. One bee, which remained, hovered and flew about in the air, allured at the same moment by the pleasing fragrance of a jasmine and a pandanus. Tell me, beautiful girl, how many bees were there? Working that out, you set up an equation and solve for the total number of bees. It's algebra dressed up in poetry and imagery. The mathematics is serious, but the presentation makes it engaging. Indian mathematics also developed sophisticated techniques for working with indeterminate equations. The Chakravala method, developed by Bhaskara and others, is a cyclic algorithm for solving Pell's equation. It's remarkably efficient and was rediscovered in Europe much later using completely different methods. When we get to the Islamic Golden Age, we're talking about one of the most incredible periods of intellectual flourishing in human history. Baghdad, under the Abbasid Caliphate, was the place to be if you were a scholar. The House of Wisdom, Beit al-Hikmah, was founded by Caliph al-Mamun in the early 9th century as a center for translation and scholarship. Greek texts were translated into Arabic. Indian mathematical works were translated. Persian and other traditions were incorporated. And scholars from all backgrounds, Muslim, Christian, Jewish, Zoroastrian, worked together, building on everything that came before. Al-Khwarizmi worked at the House of Wisdom. His algebra book was revolutionary because it was systematic and accessible. He wasn't trying to solve particular hard problems like Diophantus. He was saying, here's a general method that works for whole classes of problems. Anyone can learn this. The 6 types of equations he considered seem weird to us because we're used to negative numbers and 0, but at the time, those weren't accepted. So x squared equals 5x is a different type from x squared plus 5x equals 14, which is different from x squared plus 14 equals 5x. You have to consider each case separately. Al-Khwarizmi didn't just give algebraic solutions. He also gave geometric demonstrations showing why the methods work. This was important for legitimacy. People trusted geometry more than pure algebra at that point. After Al-Khwarizmi, other Islamic mathematicians extended and refined algebra. Abu Kamil wrote a commentary expanding on Al-Khwarizmi's work and including more sophisticated problems. Al-Karaji started working more symbolically, moving toward what we'd recognize as polynomial algebra. Omar Khayyam, yes, the same Omar Khayyam who wrote the Rubaiyat, those famous poems, was an accomplished mathematician. His work on cubic equations used conic sections to find geometric solutions. He couldn't solve them algebraically with radicals. Nobody could at that point, but he could construct solutions geometrically by finding where certain curves intersect. This geometric approach to cubics was actually quite sophisticated. It required a deep understanding of the properties of parabolas, hyperbolas, and circles. And while it didn't give numerical answers directly, it proved that solutions existed and gave a way to construct them. Islamic mathematics also made huge contributions to trigonometry, which is deeply connected to algebra. The modern definitions of sine and cosine were developed by Islamic mathematicians. They created extensive trigonometric tables that were used for astronomy and navigation, and all of this knowledge spread. When Christian Europe started conquering Islamic territories in Spain and elsewhere during the Reconquista, they found libraries full of mathematical and scientific works. Scholars like Gerard of Cremona in the 12th century translated dozens of Arabic mathematical texts into Latin. This is how European mathematicians learned about Hindu-Arabic numerals, the number system we use today. Roman numerals are terrible for calculation. Try multiplying 27 times 43 using Roman numerals. It's a nightmare. But with Hindu-Arabic numerals, you can use the standard algorithms we learn in elementary school. Leonardo Fibonacci, who we mentioned earlier, was the main champion of this new number system in Europe. His Liber Abaci, published in 1202, is full of practical problems showing how much easier calculations are with the new numerals. One of Fibonacci's problems introduced what we now call the Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, and so on, where each number is the sum of the previous two. He posed it as a problem about rabbit breeding, but the sequence turns out to appear all over nature and mathematics. Fibonacci numbers show up in the arrangement of leaves on a stem, in the spiral patterns of sunflower seeds and pine cones, in the breeding patterns of bees, and in countless mathematical contexts. The ratio of consecutive Fibonacci numbers approaches the golden ratio, about 1.618, which appears in art, architecture, and nature. But Fibonacci's real contribution was evangelizing the Hindu-Arabic system and algebraic methods to Europe. Before him, European mathematics was stuck using awkward notation and limited techniques. After him, things started to accelerate. By the Renaissance, mathematics was becoming professionalized in a different way. Universities were being established. There were chairs in mathematics, and there was this culture of mathematical competition that drove a lot of innovation, including the drama around solving the cubic. Let's talk more about that whole mess, because it's such a great story and it reveals a lot about how mathematics was done in that era. Scipione del Ferro was a professor at Bologna, one of the oldest universities in the world. He'd figured out how to solve depressed cubics without an x squared term. This was huge because these equations came up in practical problems and nobody had been able to solve them before. But Del Ferro kept it secret. Why? Because in Renaissance Italy, your academic career depended on your reputation, and your reputation depended on being able to solve problems that others couldn't. If you revealed your methods, anyone could use them, and you'd lose your edge. So Del Ferro taught his method to only a handful of trusted students, including Antonio Fior. When Del Ferro died in 1526, Fior inherited this secret weapon, and in 1535 he decided to use it. Mathematical competitions worked like this. Each person would pose a set of problems to the other. You'd have a certain amount of time, often 30 days, to solve them. Whoever solved more of the other person's problems won. There would be prize money involved, and more importantly, prestige. Fior challenged Tartaglia, figuring he had an unfair advantage with Del Ferro's secret method. He'd pose cubic equations, which Tartaglia wouldn't be able to solve, while he could easily solve whatever Tartaglia threw at him. But Tartaglia was no fool. When he saw the types of problems Fior was posing, he realized there must be a general method, and in a burst of intense work right before the deadline, Tartaglia figured it out. He discovered the same method Del Ferro had found independently. On the day of the competition, Tartaglia solved all 30 of Fior's problems in just 2 hours. Meanwhile, Fior couldn't solve any of Tartaglia's. It was a complete humiliation for Fior. This made Tartaglia famous, but he also kept his method secret. Same reason as Del Ferro. It was valuable as a competitive advantage. He did share it privately with a few people, but he encoded it in a poem to make it harder to steal. The poem goes something like, when the cube and the things together are equal to some discrete number, find 2 other numbers differing in this one. Then you will keep this as a habit that their product should always be equal, exactly to the cube of a third of the things, and so on. This is giving the formula, but in a deliberately obscure way. You'd have to already kind of know what it was talking about to understand it. Enter Cardano. Girolamo Cardano was this larger-than-life figure. He was a doctor, and a good one, sought after by nobility across Europe. He was a mathematician. He was an astrologer, and not ashamed of it, even though by this time some intellectuals were starting to see astrology as superstition. He was also a compulsive gambler, which led him to write one of the first books on probability theory. And he was writing a comprehensive book on mathematics that he hoped would be his masterpiece. Cardano heard about Tartaglia's triumph and wanted the cubic formula for his book. He wrote to Tartaglia, flattering him, promising him introductions to important patrons, basically doing everything he could to get Tartaglia to share the secret. Finally, Tartaglia agreed, but only on the condition that Cardano swear a solemn oath not to publish it. Cardano swore on the Gospels that he wouldn't publish Tartaglia's method until Tartaglia himself had published it first. Cardano and his student Ferrari then spent years working on the problem. They figured out how to extend Tartaglia's method, which only worked for depressed cubics, to work for all cubics. The trick is reducing a general cubic to a depressed cubic by a substitution. And Ferrari made another breakthrough. Using similar ideas, he figured out how to solve quartic equations, fourth-degree equations. This had never been done before. It was a major advance. But Cardano couldn't publish because of his oath. Then came the trip to Bologna in 1542. Cardano and Ferrari examined Del Ferro's papers held by his nephew. There it was, the same formula that Tartaglia had discovered, but dated 20 years earlier. Cardano decided this absolved him of his oath. He wasn't publishing Tartaglia's discovery, he was publishing Del Ferro's. So in 1545, the Ars Magna came out. To be fair to Cardano, he did give full credit to everyone involved. The title page mentions Tartaglia. In the text, he explains who discovered what and when. He acknowledges Del Ferro as the original discoverer and Tartaglia as an independent discoverer. He credits Ferrari for the quartic. But Tartaglia didn't see it that way. He felt betrayed. He published pamphlets attacking Cardano's character, calling him an oath breaker and worse. Cardano didn't respond directly, but Ferrari did. Ferrari defended his teacher and challenged Tartaglia to a debate. The exchange of pamphlets back and forth is pretty entertaining if you read it today. These guys did not hold back. Tartaglia accused Ferrari of being Cardano's puppet, of not having original ideas. Ferrari shot back with detailed mathematical arguments and personal insults. The public debate in Milan was supposed to settle it, but by the end of the first day, it was clear that Ferrari understood the new algebra at a much deeper level than Tartaglia. Ferrari could solve all kinds of variations and extensions. Tartaglia was still basically working with the specific formula he'd discovered. Tartaglia's decision to flee that night was probably wise. He would have been demolished on day 2, but it destroyed his reputation. Nobody wants to hire a mathematician who runs away from a challenge. The sad part is that Tartaglia was a brilliant mathematician who made genuine contributions beyond the cubic. He translated Euclid and Archimedes into Italian, making these texts accessible to Italian readers. He worked on ballistics and the paths of cannonballs. He contributed to surveying and practical mathematics, but he's remembered primarily for the cubic equation drama, and not in a good way. Meanwhile, we call it Cardano's formula, even though Cardano didn't discover it and openly said so in his book. Ferrari, for his part, went on to have a successful career. He became a professor, made good money, and died relatively young, in his early 40s, possibly poisoned by his own sister, according to some accounts. Because Renaissance Italy was dramatic in all kinds of ways, the Ars Magna is genuinely impressive beyond just the cubic and quartic formulas. Cardano worked through 13 different types of cubic equations, explaining how to solve each one. He discussed the problem of multiple roots when an equation has the same solution repeated. He encountered complex numbers, and while he didn't really understand them, he noted that they seemed to appear in the formulas. That's the thing about the cubic formula. Sometimes, when you apply it, you get expressions involving the square root of negative numbers. Even when you know the equation has real number solutions, the formula might take you through imaginary numbers to get there. This was deeply confusing. How can a real number solution require you to work with impossible imaginary quantities as an intermediate step? It didn't make sense. Cardano mentioned it but couldn't explain it. Raphael Bombelli, in the 1560s, was the first to really work this out systematically. He showed that you could treat the square root of -1 as a mathematical object that follows specific rules. He worked out the arithmetic of complex numbers, how to add them, multiply them, and so on. Once you accept that I, the imaginary unit, is legitimate, complex numbers turn out to be incredibly useful. They're not just a mathematical curiosity. They're essential for understanding oscillations, waves, electrical circuits, quantum mechanics, all kinds of real-world phenomena. Every time you listen to music on a digital device, complex numbers are involved in the signal processing. When engineers design filters for audio or radio signals, they work in the complex plane. When quantum physicists calculate the behavior of particles, they use complex valued wave functions. So these imaginary numbers that Cardano encountered and didn't understand turned out to be one of the most practical concepts in all of mathematics. But it took a while for people to get comfortable with them. Well into the 19th century, some mathematicians were still uncomfortable with complex numbers and tried to avoid using them when possible. François Viet's contribution is sometimes underappreciated because his notation didn't quite catch on. He used vowels for unknowns and consonants for knowns, which is backwards from our convention. But the key insight was there. Use letters to represent quantities in general, not just specific numbers. Viet also insisted on homogeneity. All terms in an equation had to have the same dimensional power. This seems like a restriction to us, but Viet saw it as maintaining rigor. You can't add a length to an area. They're different types of quantities. This homogeneity requirement meant that Viet's equations looked weird. He'd write things like a cubed plus b plane in A equals z solid, meaning a cubed plus ba squared equals z, where a is a length, b is a length, BA squared is an area times a length, a volume, and Z is a volume. Everything has to work out dimensionally. This seems unnecessary and cumbersome now, but Viet was trying to ground algebra in geometric reality. He wanted the same level of rigor for algebra that geometry had achieved. Descartes dropped this requirement. In La Géométrie, he said essentially that we can think of all these quantities as numbers and not worry about their geometric interpretation. This liberated algebra to deal with higher degree equations and more complex manipulations. Descartes' other huge contribution was showing that geometric curves can be described by algebraic equations. A circle is all the points where x squared plus y squared equals r squared. An ellipse is all the points where the sum of distances to two fixed points is constant, which gives you an algebraic equation. This means you can solve geometric problems using algebra. Want to find where two curves intersect? Set their equations equal and solve for x and y. Want to find the tangent line to a curve at a point? That's a problem you can attack algebraically. This fusion of geometry and algebra, analytic geometry, opened up entirely new possibilities. It made calculus possible. Newton and Leibniz, developing calculus later in the 17th century, relied heavily on analytic geometry. Calculus is, in a sense, the study of how things change, rates of change, accumulation over time, and you can express these ideas algebraically. The derivative of x squared is 2x. The integral of 2x is x squared. These relationships can be studied using algebraic manipulation. So algebra and calculus grew up together in the 17th and 18th centuries. Mathematicians like Euler, de Bernoulli, and Lagrange used algebra to solve problems in calculus, mechanics, and astronomy. Euler in particular was incredibly prolific. He wrote so many papers and books that they're still being published from his archives. He worked in every area of mathematics known at the time and created several new areas. His notation, like using e for the base of natural logarithms, I for the imaginary unit, f of x for functions, these became standard because Euler used them. Euler's identity, e to the power of I times pi plus 1 equals 0, is often called the most beautiful equation in mathematics. It connects 5 of the most important constants, e, pi, 1, and 0, in a simple, elegant relationship. It's a profound connection between exponential functions and trigonometry that's fundamental to complex analysis. But back to the quintic problem. By the late 18th century, mathematicians had solved equations up to the 4th degree. Surely the 5th degree was next, right? Lagrange worked on it extensively. In his 1770 paper, Reflections on the Algebraic Solution of Equations, he analyzed why the methods for cubics and quartics worked. He realized it had to do with finding auxiliary equations, resolvents, of lower degree. For a cubic, you can reduce the problem to solving a quadratic resolvent. For a quartic, you can reduce it to solving a cubic resolvent. So, if you can solve quadratics and cubics, you can solve quartics. Logically, you'd think that for a quintic, you'd reduce it to solving a quartic resolvent. But when Lagrange tried this, he found that the resolvent ended up being degree 6 or higher than the original equation. This didn't help at all. This was the first hint that something fundamentally different might be going on with quintics, but Lagrange couldn't prove they were unsolvable. He just showed that the previous methods didn't generalize. Paolo Ruffini, an Italian mathematician and medical doctor, claimed in 1799 to have proven that the general quintic cannot be solved by radicals. His proof was long and complicated, and it had some gaps. Some mathematicians accepted it, but many were skeptical. Then Niels Henrik Abel came along. Abel was Norwegian, from a poor family, and didn't have access to the best mathematical education growing up. But he was brilliantly talented and basically taught himself advanced mathematics by reading Euler and other masters. Abel's proof that the general quintic is unsolvable was published in 1824. It was rigorous and convincing. Abel showed that you cannot write a formula using only radicals, square roots, cube roots, and so on, that solves every quintic equation. This was a paradigm shift. Mathematics had proven something was impossible. Not just unknown, but genuinely impossible. No matter how clever you are, you will never find such a formula, because it doesn't exist. But, as I mentioned, Abel's proof didn't explain why some specific quintics are solvable, like x to the fifth equals 32 can be solved. Just take the fifth root of 32, and x to the fifth minus x equals 0 can be solved. Factor it as x times the quantity x to the fourth minus 1. Galois's insight was to look at the symmetries of the roots. Given a polynomial equation, you can consider all the ways of permuting its roots that preserve certain relationships between them. These permutations form a group, the Galois group of the equation. If this group has a certain structure, being solvable in the group theory sense, then the equation can be solved by radicals. The groups associated with equations of degree 4 or less are always solvable. The group associated with the general quintic, the symmetric group on 5 elements, is not solvable. This is why some quintics can be solved and others can't. It depends on the specific Galois group of that particular equation. Galois' insight was incredibly deep. He was seeing connections between disparate areas of mathematics that nobody had seen before. He was creating a whole new framework for understanding polynomial equations. But his life was tragic. He was politically radical at a time of political turmoil in France. He was arrested and imprisoned for political activities. He was in and out of jail, struggling to get his mathematical work recognized. The story of his last night is heartbreaking. He knew he was likely to die the next day. Whether the duel was over a woman, or political, or a trap, we don't know for sure. But Galois spent the night writing, trying to get down as much as he could about what he'd discovered. In the margins, he kept writing, "Je n'ai pas le temps, I have no time." There was so much more he wanted to explain, but dawn was coming. He was shot in the stomach, left in a field, found by a peasant, taken to a hospital, and died the next day. He was 20 years old. He never saw his ideas fully understood and appreciated. His papers sat in a drawer for years. When they were finally published, most mathematicians couldn't make sense of them. The ideas were too new, too abstract. Joseph Louville, who published Galois' work in 1846, wrote admiringly about it, but didn't fully grasp the group theoretic aspects. He saw that Galois had answered the question of solvability, but missed how revolutionary the method was. It wasn't until Camille Jordan's work in 1870 that Galois theory started to be properly understood. Jordan wrote extensively about permutation groups and their applications to equations. He reformulated and clarified Galois' ideas, making them accessible to other mathematicians. Slowly, throughout the late 19th century, Galois theory was developed and extended. Mathematicians realized that this framework of connecting group theory to field theory was incredibly powerful and could be applied to many problems beyond just polynomial equations. The tragic irony is that Galois, who died thinking his work would be lost and forgotten, ended up having an enormous impact on mathematics. Galois theory is now a standard part of graduate mathematics education. Group theory has become one of the central subjects in modern mathematics, and the questions Galois' work raised led to whole new areas of research. Abstract algebra as a discipline grew out of trying to understand and generalize the ideas Galois had introduced. Richard Dedekind, working in the late 19th century, made rigorous the concepts that earlier mathematicians had used intuitively. What exactly is a number? What is an integer? What is a field? Dedekind gave precise definitions. He invented ideals as a way to generalize the concept of divisibility in number systems that don't behave like the ordinary integers. This turned out to be crucial for algebraic number theory. He also worked on axiomatizing set theory and understanding the foundations of mathematics. This project, making mathematics rigorously logical from the ground up, was a major theme of late 19th and early 20th century mathematics. David Hilbert continued this project. At the International Congress of Mathematicians in 1900, Hilbert presented a list of 23 problems that he thought would drive mathematics in the 20th century. Many of them were about algebra, number theory, and foundations. Hilbert's program was to axiomatize all of mathematics, proving it was consistent and complete. Gödel's incompleteness theorems, proved in 1931, showed this was impossible. There are limits to what can be proven within any consistent mathematical system. But the effort to achieve Hilbert's program led to huge advances in logic, set theory, and abstract algebra. Emmy Noether was a student of one of Hilbert's colleagues, and she became one of the most important algebraists of the 20th century. Noether's approach was to identify the essential abstract structures underlying various mathematical phenomena and then prove theorems at that level of abstraction. She worked on ring theory, showing how ideals could be factored uniquely, generalizing the unique factorization of integers into primes. She worked on representation theory, understanding how abstract groups can be realized as groups of matrices or other concrete objects. Noether also proved fundamental theorems connecting symmetry to conservation laws in physics. Noether's theorem says that every continuous symmetry of a physical system corresponds to a conserved quantity. Time symmetry gives conservation of energy. Space symmetry gives conservation of momentum. This is now fundamental to theoretical physics, but Noether faced enormous discrimination as a woman. She couldn't get a proper academic position for years because universities wouldn't hire female professors. She lectured under Hilbert's name. She was paid very little. When the Nazis came to power, she was forced to flee Germany because she was Jewish. Eigenvalues and eigenvectors, special vectors that are only scaled, not rotated by a transformation, turn out to be fundamental in physics, engineering, data science, everywhere. Google's PageRank algorithm, which made Google successful, is based on finding the principal eigenvector of a huge matrix representing the web. Modern cryptography relies heavily on abstract algebra and number theory. The RSA encryption algorithm, which secures most internet traffic, uses properties of modular arithmetic and prime numbers. Elliptic curve cryptography uses the group structure of points on elliptic curves. These are not easy concepts. The math involved is graduate-level abstract algebra. But billions of people use these algorithms every day without thinking about the mathematics underlying them. Coding theory, the mathematics of error correction, uses linear algebra and finite fields. Your CD can have scratches and still play music because of Reed-Solomon codes, which use polynomial algebra over finite fields to detect and correct errors. Quantum computing, which is still in early stages of development but holds enormous promise, relies on linear algebra over complex numbers. A quantum computer manipulates quantum states, which are vectors in complex vector spaces. Quantum algorithms are described as operations on these spaces. The classification of finite simple groups, completed in the 1980s, though there have been some gaps filled in more recently, was a massive collaborative effort. Finite simple groups are the building blocks from which all finite groups are constructed, like prime numbers are the building blocks for integers. The classification theorem says there are 18 infinite families of simple groups plus 26 exceptional groups called sporadic groups. The proof spans tens of thousands of pages across hundreds of papers by dozens of mathematicians. It's one of the largest collaborative proofs in history. Some of these sporadic groups are incredibly large and complicated. The monster group has about 8 times 10 to the power of 53 elements. Working with objects this large requires sophisticated computational methods and deep theoretical understanding. But knowing this classification is useful. It tells you what the possibilities are. When you encounter a finite group in some context, you can use the classification to understand its structure and properties. In algebraic topology, homology and cohomology groups let you study the shape of spaces using algebra. A space might be too complicated to visualize directly, but you can compute its homology groups, which are algebraic objects, and use those to understand the space's properties. This has applications in data analysis. Topological data analysis uses ideas from algebraic topology to find structure in high-dimensional datasets. You can't visualize data in 100 dimensions, but you can compute topological features and use those to understand the data. Representation theory, the study of how abstract groups can be realized as groups of matrices, connects abstract algebra to linear algebra and has applications in physics, chemistry, and other sciences. When chemists study molecular symmetries, they're using representation theory. Lie theory, the study of continuous symmetry groups called Lie groups, is fundamental in physics. The symmetries of space-time, the symmetries of quantum fields, the gauge symmetries underlying the standard model of particle physics All of these are Lie groups. Algebraic geometry studies geometric objects using commutative algebra and has become essential in many areas of mathematics and theoretical physics. String theory, which tries to unify quantum mechanics and general relativity, uses sophisticated algebraic geometry. The Langlands program, initiated by Robert Langlands in the 1960s, proposes deep connections between number theory, representation theory, and algebraic geometry. It's an incredibly ambitious framework that, if fully realized, would unify large swaths of mathematics. Some parts of the Langlands program have been proven, like the modularity theorem, which was the key step in Andrew Wiles's proof of Fermat's last theorem. But much of the program remains conjectural and is the subject of active research. All of this, the abstraction, the generalization, the search for deep connections, traces back to that basic algebraic impulse. Find the pattern, see the structure, understand why things work the way they do. When the Babylonians developed methods for solving equations, they were looking for patterns in how to manipulate those equations. When Brahmagupta worked out rules for negative numbers, he was finding structure in arithmetic. When Galois studied the symmetries of roots, he was uncovering deep connections between seemingly different areas. This is what algebra is about. Not just solving for x, though that's part of it, but seeing past the specific problem to the general principle, understanding structure, finding connections. And the beautiful thing is, we're still doing it. Every generation of mathematicians thinks they've figured out algebra, and then the next generation finds new structures, new connections, new levels of abstraction. We've gone from word problems on clay tablets to abstract category theory, from dividing estates to quantum computing, from negative numbers being controversial to complex algebras being routine. And there's no sign of it stopping. New mathematical structures are being discovered and studied. New connections are being found. New applications are emerging. Maybe in 100 years, what we consider advanced abstract algebra will seem as elementary as basic arithmetic seems to us. Maybe there are levels of abstraction we haven't even imagined yet. That's the trajectory of algebra. Always pushing further, always abstracting more, always finding new patterns and structures. Always asking not just what is the answer, but why does this work and what's the general principle? From Babylon to Baghdad to Bologna to Burlington, from clay tablets to quantum computers, algebra has been humanity's way of understanding structure and pattern, and that journey is far from over. Let's talk about some of the other fascinating threads in algebra's history that don't always get the spotlight they deserve. Because there are so many brilliant mathematicians and interesting ideas that we haven't covered yet. Take the development of Boolean algebra, for instance. George Boole, in the mid-19th century, realized you could create an algebra where the basic operations aren't addition and multiplication of numbers, but logical operations like AND, O, and NOT. In Boolean algebra, you work with true and false values instead of numbers. A and B is true only if both A and B are true. A or B is true if at least one of them is true. Not A flips true to false and vice versa. This might seem like a curiosity, but it turned out to be fundamental for computer science. Every digital circuit every computer program, every search query you type into Google, all of it ultimately comes down to Boolean logic. When you search for algebra and history, not calculus, you're using Boolean operators. When a computer chip adds two numbers, it's using circuits built from Boolean logic gates. The entire digital revolution rests on ideas from Boolean algebra. Boole himself didn't foresee this. He was thinking about logic and philosophy, trying to put reasoning on a mathematical foundation. The practical applications came much later, after Claude Shannon showed in his 1937 master's thesis that Boolean algebra could be used to design electrical circuits. Then there's the development of matrix algebra. Matrices, rectangular arrays of numbers, were used by Chinese mathematicians 2,000 years ago for solving systems of linear equations. But they didn't think of matrices as mathematical objects in their own right. In the 19th century, Arthur Cayley and James Joseph Sylvester developed matrix algebra as a subject. They showed that matrices could be added and multiplied according to specific rules, and that this matrix algebra had interesting properties. Matrix multiplication is weird when you first encounter it. It's not commutative. A times B doesn't always equal B times A. But it turns out this non-commutativity is exactly what you need for representing compositions of geometric transformations, changes of coordinate systems, quantum mechanical operators, and many other things. Determinants, special numbers you can calculate from square matrices, were studied even earlier. They arise naturally when solving systems of linear equations using Cramer's rule. But mathematicians gradually realized that determinants have deep geometric and algebraic significance. The determinant tells you the volume scaling factor of the linear transformation represented by the matrix. A determinant of 0 means the transformation squashes space down to lower dimension. It's not invertible. These geometric insights came from studying the algebra. Eigenvalues and eigenvectors, which I mentioned earlier, were discovered in the context of studying quadratic forms and differential equations. But they turned out to be fundamental throughout mathematics and science. In quantum mechanics, observable quantities correspond to operators, and the possible values you can measure are the eigenvalues of those operators. The quantum states are eigenvectors. This isn't just a mathematical formalism, it's deeply connected to the physics. In data science and machine learning, principal component analysis finds the eigenvectors of a covariance matrix to identify the directions of maximum variance in data. Google's PageRank finds the dominant eigenvector of the web graph. Eigenvalues show up everywhere. The development of vector spaces as abstract algebraic structures came later. Instead of thinking concretely about arrows in space or lists of numbers, mathematicians abstracted the key properties. A vector space is any set where you can add elements and multiply them by scalars, satisfying certain axioms. This abstraction turns out to be incredibly powerful. Polynomials form a vector space. Functions form a vector space. Solutions to differential equations form a vector space. Once you recognize something as a vector space, you can apply all the tools of linear algebra. The study of algebras, which is a loaded term, I know, as algebraic structures came about in the 19th century too. An algebra in this technical sense is a vector space that also has a multiplication operation compatible with the vector space structure. The real numbers form an algebra. The complex numbers form an algebra, but there are other algebras too. The quaternions, discovered by William Rowan Hamilton in 1843, are a four-dimensional algebra where multiplication is non-commutative but still associative. Hamilton was trying to extend complex numbers to 3 dimensions and couldn't make it work. Then one day, walking with his wife along a canal in Dublin, he suddenly realized it would work in 4 dimensions. He was so excited that he carved the defining equations into a stone on the bridge. The graffiti is gone now, but there's a plaque commemorating the spot. Quaternions turned out to be useful for describing rotations in 3-dimensional space. They're used in computer graphics, robotics, and aerospace engineering. There's even a whole theory of quaternionic analysis extending complex analysis to 4 dimensions. Octonions, discovered later, are an 8-dimensional algebra where even associativity fails. They're weird and wonderful, with connections to string theory and exceptional Lie groups. The Cayley-Dixon construction shows you how to double the dimension repeatedly. Real numbers, 1 dimension to complex numbers, 2 dimensions to quaternions, 4 dimensions to octonions, 8 dimensions and beyond, but you lose properties at each step. The real numbers are ordered. Complex numbers aren't ordered, but are commutative. Quaternions aren't commutative, but are associative. Octonions aren't even associative. This pattern that, as you generalize and extend, you sometimes have to give up nice properties, is a recurring theme in algebra. You can't have everything. There are trade-offs. The theory of fields, not in the physics sense, but in the algebra sense, is another major strand. A field is a set where you can add, subtract, multiply, and divide, except by 0, satisfying the usual rules. The rational numbers form a field. The real numbers form a field. The complex numbers form a field, but there are also finite fields, fields with only finitely many elements. The simplest finite field has just 2 elements, 0 and 1. Addition and multiplication work mod 2, so 1 plus 1 equals 0. This is the field used in computer arithmetic and coding theory. There are finite fields of any prime power size. The field with 5 elements, the field with 8 elements, the field with 27 elements. These are used in coding theory, cryptography, and finite geometry. Galois, who we talked about earlier, didn't just study groups. He also studied field extensions, larger fields containing a given field. This is essential to Galois theory. The Galois group of an equation is related to the field extension generated by adjoining the roots of the equation. This might sound abstract, but it has concrete consequences. Whether you can construct something with compass and straight edge is a question about field extensions. The ancient Greek problems, doubling the cube, trisecting an angle, squaring the circle, turn out to be impossible because the required numbers don't lie in the right field extensions. Pierre Wansel proved in 1837 that doubling the cube and trisecting an angle are impossible with compass and straight edge. Ferdinand von Lindemann proved in 1882 that squaring the circle is impossible. This required showing that pi is transcendental, not the root of any polynomial equation. These impossibility proofs were major achievements. They showed that problems mathematicians had worked on for over 2,000 years simply could not be solved with the specified tools. It wasn't that people weren't clever enough, it was genuinely impossible. This is the power of algebra. It doesn't just solve problems, it can prove when solutions don't exist. It reveals the structure of what's possible and what's not. The theory of ideals, which Dedekind introduced, generalizes the concept of divisibility. In the ordinary integers, you can factor any number uniquely into primes, but in some other number systems, unique factorization fails. Dedekind showed that you could restore unique factorization by working with ideals instead of individual numbers. An ideal is a subset of a ring satisfying certain properties. Ideals can be multiplied and factored uniquely, even when individual elements can't. This was a huge insight. It meant that number theorists could work in algebraic number fields, extensions of the rationals, without losing the ability to factor. This was crucial for attacking problems like Fermat's last theorem. Amy Noether and her student took this further, developing the general theory of rings and ideals. They identified different types of rings: Noetherian rings, Dedekind domains, unique factorization domains, based on how well unique factorization works. This classification helps you know what techniques will work in what contexts. If you know your ring is Noetherian, certain theorems apply. If it's a Dedekind domain, other theorems apply. The abstract theory gives you a map of the landscape. Module theory is another generalization. A module is like a vector space, but instead of multiplying by numbers from a field, you multiply by elements from a ring. This extra generality makes modules more complicated, but also more versatile. Modules arise naturally when studying representations of groups, when doing algebraic topology, when working with number fields. The category of modules over a ring is a fundamental object of study in abstract algebra. Homological algebra, which developed in the mid-20th century, studies modules and more general algebraic objects using derived functors, exact sequences, and other tools. It's quite abstract, but has applications in algebraic topology, algebraic geometry, representation theory, and beyond. The interplay between algebra and topology has been particularly fruitful. Algebraic topology uses algebra to study topological spaces. Homology groups, cohomology groups, fundamental groups, these are algebraic invariants that capture topological features. Two spaces that are homomorphic, topologically the same, have isomorphic homology groups. So if you can show the homology groups are different, you've proven the spaces are topologically distinct. This gives you a way to prove impossibility results in topology. The Brouwer fixed point theorem: every continuous map from a disk to itself has a fixed point, can be proved using homology. Many other topological theorems rely on algebraic methods. Going the other way, topological ideas have influenced algebra. Topological groups, topological vector spaces, topological rings, these combine algebraic and topological structure. The topology says which operations are continuous, which sequences converge. This is essential in functional analysis, where you study infinite dimensional vector spaces of functions. the space of continuous functions, the space of square integrable functions, the space of smooth functions. These are all infinite dimensional vector spaces with topologies. Operator algebras, studied in functional analysis, are algebras of operators on Hilbert spaces. These arise in quantum mechanics and have deep connections to other areas of mathematics. Von Neumann algebras and C-star algebras are two major types. The whole theory of operator algebras was developed in the 20th century and has led to surprising connections between quantum mechanics and knot theory, between group theory and geometry, between analysis and algebra. Differential algebra is another variation, studying differential rings and differential fields, where you have a differentiation operation satisfying the product rule. This has applications in studying differential equations and their solutions. Algebraic number theory is the study of number fields and their rings of integers. These are extensions of the rational numbers, like the field generated by the square root of 2 or the cube root of 5. Questions about Diophantine equations often come down to understanding these number fields. Fermat's last theorem, which says x to the n plus y to the n equals z to the n, has no non-zero integer solutions for n greater than 2, was finally proved by Andrew Wiles using the theory of elliptic curves and modular forms. The proof is incredibly sophisticated, using ideas from algebraic geometry, representation theory, and number theory. It's built on work by many mathematicians over decades. Wiles's insight was to connect elliptic curves to modular forms in a way that let him prove enough cases to finish the theorem. Algebraic geometry studies geometric objects, curves, surfaces, higher dimensional varieties using algebra. A curve in the plane can be described by a polynomial equation in two variables. The zeros of this polynomial are the points on the curve. You can then study the curve by studying the polynomial, or more accurately, by studying the ring of all polynomials that vanish on the curve. This ring encodes geometric information about the curve. This might seem backwards, using algebra to study geometry, but it's incredibly powerful. Algebraic geometry has become one of the central areas of mathematics, with connections to number theory, topology, mathematical physics, and more. Scheme theory, developed by Alexander Grothendieck in the 1950s and 60s, revolutionized algebraic geometry by working at an even more abstract level. A scheme is like a geometric object, but it's defined in terms of its ring of functions. This abstraction allowed Grothendieck and others to prove theorems that had resisted earlier approaches. It also revealed deep connections, like the Weil conjectures, which connect topology and number theory through algebraic geometry. The Weil conjectures were finally proved by Pierre Deligne in 1973 using Grothendieck's machinery plus new ideas. This was a major achievement, solving problems that had been open for decades. Non-commutative geometry, pioneered by Alain Connes, goes even further. What if your space is so exotic that the algebra of functions on it is non-commutative? Can you still do geometry? Connes showed that yes, you can. Non-commutative geometry has applications to quantum physics, where position and momentum don't commute. It also connects to number theory and other areas in unexpected ways. The idea that geometry and algebra are two faces of the same coin, that you can translate between them freely, is one of the great insights of modern mathematics. Descartes started it with analytic geometry. Grothendieck took it to new heights, and the interplay continues to drive research today. Representation theory studies how abstract algebraic objects, groups, algebras, Lie algebras can be represented as matrices or linear transformations. This makes the abstract concrete and allows you to use linear algebra techniques. Fourier analysis, which breaks functions down into sums of simple waves, is representation theory of certain groups. The discrete Fourier transform, used in digital signal processing, is a representation of a cyclic group. Character theory, developed in the late 19th and early 20th centuries, uses the traces of representation matrices to study groups. Characters satisfy orthogonality relations that let you decompose representations and understand group structure. This has applications in chemistry and physics. The symmetry groups of molecules can be studied using character theory to predict spectroscopic properties. The representations of the rotation group describe angular momentum in quantum mechanics. The representation theory of Lie groups and Lie algebras is even richer. Irreducible representations, those that can't be broken into simpler pieces, are classified for many important Lie groups. This classification is essential for particle physics. The standard model of particle physics uses gauge groups, special types of Lie groups, to describe fundamental interactions. The symmetries of these groups determine which particles and interactions are possible. When physicists discovered the Higgs boson in 2012, they were confirming a prediction based on the mathematics of gauge theory and representation theory. The algebra was predicting the physics. This is one of the most remarkable things about mathematics. Ideas developed for purely abstract reasons often turn out to describe reality. Group theory was created to understand polynomial equations. It ended up describing particle physics. Complex analysis was developed to understand functions of a complex variable. It turned out to be essential for understanding fluid flow, electrical circuits, and quantum mechanics. Differential geometry, which studies curves and surfaces, became the language of general relativity. Einstein's field equations, describing gravity as curved spacetime, are equations in differential geometry. The unreasonable effectiveness of mathematics in the natural sciences, as Eugene Wigner put it, is one of the deep mysteries. Why should abstract algebraic structures invented by humans correspond to structures in the physical universe? Nobody knows the answer. Maybe we're discovering mathematical structures that are really there in nature. Maybe we're inventing structures and then finding that some of them happen to fit reality. Maybe mathematics is just the language our brains use to understand patterns, and reality is full of patterns. Whatever the reason, algebra keeps proving useful in unexpected ways. Ideas from abstract algebra are now used in data science, machine learning, and artificial intelligence. They're used in computer graphics and animation. They're used in cryptography and network security. When you use WhatsApp or Signal to send an encrypted message, you're relying on elliptic curve cryptography. When Netflix recommends a movie, matrix factorization algorithms are at work. When you play a video game with realistic physics, quaternions are probably involved. The algebra we teach in high schools, solving linear equations, factoring polynomials, using the quadratic formula, is just the tip of an enormous iceberg. It's basic literacy in the language of structure and pattern, and that language has grown incredibly expressive over the centuries. We can talk about spaces with infinitely many dimensions. We can talk about symmetries of quantum fields. We can talk about categories of categories of categories. Some of this is undeniably esoteric. Not everyone needs to understand sheaf cohomology or derived functors, but the basic impulse, finding patterns, understanding structure, seeing connections, that's universal. Every time you notice that some process repeats, that some pattern recurs, that some structure underlies diverse phenomena, you're thinking algebraically. You're participating in this ancient tradition of seeing beyond the surface. The Babylonians noticed that certain problems about land and loans had the same structure, even though they were about different things. That's algebraic thinking. Al-Khwarizmi noticed that different-looking equations could be solved by the same method if you transformed them properly. That's algebraic thinking. Galois noticed that the solvability of equations was really about the structure of symmetry groups. That's algebraic thinking. Noether noticed that diverse theorems in different areas of algebra were really special cases of more general principles about ideals. That's algebraic thinking, and we're still doing it, still finding new structures, new patterns, new connections. The field is alive and growing. Modern areas like tropical geometry, which studies a modified arithmetic where addition is replaced by minimum and multiplication by addition, are revealing new structures. Derived algebraic geometry, which studies spaces equipped with additional chain complex data, is uncovering new phenomena. Higher category theory, which iterates the concept of category to study categories of categories and beyond, is providing new frameworks for understanding mathematics. Homotopy type theory is trying to build foundations of mathematics based on ideas from topology and category theory. It's a radical rethinking of what mathematical reasoning could look like. Quantum groups and quantum algebras, despite their names, are purely mathematical objects that deform classical algebraic structures in interesting ways. They have connections to knot theory, representation theory, and mathematical physics. Cluster algebras, discovered around the year 2000, have unexpected connections to diverse areas: representation theory, Teichmüller theory, integrable systems, and more. Each generation discovers new structures that the previous generation never imagined, and each time these structures turn out to have unexpected connections to other mathematics and sometimes to physics or other sciences. This is why mathematicians keep abstracting, keep generalizing, keep looking for deeper structures, because history shows that today's abstraction is tomorrow's application. Today's pure mathematics is tomorrow's physics, or computer science, or engineering. When Hardy wrote in his autobiography that he'd never done anything useful, he was wrong. His work in number theory ended up being crucial for cryptography. His work in analysis is used in signal processing, Ramanujan's bizarre formulas about infinite series and theta functions seemed like pure curiosity. They are now used in string theory and other areas of theoretical physics. The list goes on. Pure mathematics becomes applied mathematics, often in ways nobody anticipated. So what's the lesson from all of this history? What's the takeaway from 5,000 years of algebra? I think it's that abstraction is powerful. Seeing past the details to the underlying structure gives you leverage. Once you understand structure, you can apply that understanding in many contexts. It's that collaboration across cultures and eras matters. The algebra we have today is built on contributions from Babylon, Egypt, Greece, India, China, the Islamic world, Europe, and everywhere else. No one culture, no one era has all the answers. It's that seemingly impossible problems sometimes have surprising solutions. The quintic equation seemed impossible to solve until Galois realized it was about groups, not formulas. Fermat's last theorem seemed impossible until Wiles connected it to elliptic curves and modular forms. It's that mathematics is cumulative. We stand on the shoulders of giants. Descartes built on Viette, Galois built on Lagrange, Noether built on Dedekind. Each generation extends what came before. And it's that mathematics is a human endeavor. Real people with their quirks, their struggles, their moments of insight and despair created these ideas. Tartaglia fleeing a debate, Galois writing frantically before a duel, Noether facing discrimination but persevering anyway. These weren't just abstract minds producing theorems. They were humans trying to understand the world, trying to solve problems, trying to see patterns, and that makes mathematics more approachable. You don't have to be a superhuman genius to think algebraically. You just have to be willing to look for patterns, to question why things work, to seek structure. Maybe you won't discover a new type of group or prove a major theorem, but you can understand the basic ideas. You can appreciate the beauty of the structures that have been discovered. You can use algebraic thinking in your own life and work, because at its core, algebra is about understanding relationships. How do different quantities relate to each other? How do changes in one thing affect another? What's the structure connecting these phenomena? Those are questions everyone asks, whether they use mathematical language or not. Algebra just gives us precise tools for answering them. So, the next time you see an algebraic equation, remember, you're looking at the culmination of millennia of human thought. That X represents countless attempts to understand the unknown. Those operations represent hard-won insights about structure and pattern, and the story continues. We haven't reached the end of algebra. We're still in the middle of it, still discovering, still abstracting, still finding new connections. Who knows what algebraic structures future mathematicians will study? What new connections they'll find? What applications will emerge that we can't even imagine today? That's the beauty of mathematics. It's never finished. There's always more to discover, more to understand, more to explore. From those Babylonian scribes scratching on clay to modern mathematicians working with abstract categories and homotopy types, we've come a long way. But the journey isn't over. It's just getting started.